If you try to replace a functional group on a benzene ring directly, you'll often find yourself hitting a brick wall. The carbon-nitrogen bond in aniline is notoriously stubborn. But what if there were a way to transform that stable amino group into one of the best leaving groups in all of organic chemistry? This is the magic of diazotization. It's a chemical primer that turns a simple aniline molecule into a highly reactive diazonium salt, opening a gateway to almost any aromatic compound you can imagine. Let's look at the overall transformation. We start with aniline. That's a benzene ring with an NH2 group, and we treat it with nitrous acid at freezing temperatures. The result is benzene diazonium chloride. Notice the structure of that new group. 2 nitrogen atoms locked together with a triple bond. But there's a catch. Nitrous acid is so unstable that we can't just pull it off a shelf. Instead, we have to generate it in situ, or in the flask, by mixing sodium nitrite with hydrochloric acid. Let's dive into the mechanism to see how this actually happens. First, we need to create the real star of the show, the nitrosonium ion. Think of this as the hook that will grab onto our aniline. As you can see, the acid protonates the nitrous acid, and a molecule of water leaves, leaving behind an NO cation. This nitrosonium ion is starving for electrons. Now, watch what happens when aniline enters the scene. The lone pair of electrons on the nitrogen of aniline acts like a magnet, attacking the positive nitrosonium ion. We've now joined the 2 nitrogens together, forming a N-nitroso-ammonium ion. But we aren't at that triple bond yet. To get there, we need a series of proton shifts, a process called tautomerization. Notice how the protons are shuffled around from the nitrogen to the oxygen. It's like a game of musical chairs. First, we form a double bond between the nitrogens, pushing the hydrogen over to the oxygen. Then, another proton from the acidic solution jumps onto that oxygen. Look closely at that oxygen group now. It has 2 hydrogens and a positive charge. Does that look familiar? It's a water molecule waiting to happen. And here's the key insight. In a sudden burst of stability, the nitrogen lone pair pushes down to form a triple bond, kicking that water molecule out into the solution. What we're left with is the diazonium cation. That N triple bond N structure is effectively a pressurized molecule of nitrogen gas just waiting to escape. Because nitrogen gas is so incredibly stable, it's a phenomenal leaving group. This makes the diazonium salt a universal middleman. From here, you can swap that nitrogen for a halogen, a cyanide group, or even a simple hydroxyl group to make phenol. But remember the thermometer in our diagram. All of this must happen between 0 and 5 degrees Celsius. Why? Because the moment the solution warms up, the triple bond vibrates too violently. The nitrogen gas bubbles away, and our hard-earned intermediate vanishes. So, the next time you see a complex aromatic molecule, don't just see a finished product. Look for the traces of the diazonium bridge, the clever chemical trick that turns a stubborn bond into a powerhouse of reactivity.